All right, so yesterday we finished up talking about hydrate formation where you can react aldehydes and ketones with water. Today we're going to be doing something similar but with alcohols. And so I'll show you the overall reaction where you have an alcohol nucleophile. And in fact, you saw some of this in your pod already. So you can have an aldehyde or a ketone, either one. You can react this with two equivalents of an alcohol. Typically this is done under acidic conditions, so I'll just write H plus catalytics. And what you can do is get both alcohols to attack that central carbon, and you kick off water as a byproduct. What this is called is an acetal for aldehydes, and a ketal if it's for a ketone. So if your starting material is a ketone, you form a ketal. If it's an aldehyde, you form an acetal. Some people just call all of them acetals, so it gets used somewhat in vague situations like that. All right. The important thing to note, though, is the acid that is used. So I'm going to put a little asterisk here. Common acids that are used are H2SO4, which you saw in your pod, phosphoric acid, H3PO4, or tosylic acid, TSOH. And tosylic acid looks like this, where you have a sulfur, double bonded oxygens, and an OH coming off. So that's tosylic acid. And does anybody know the reason why these acids are used? As opposed to, let's say, HCl? Think about their conjugate bases. Are their conjugate bases good nucleophiles? So for example, if tosylic acid gives up its proton, is that going to be a good nucleophile? No, it's not going to be a good nucleophile, and that's the whole idea, is you don't want your conjugate base to end up attacking your aldehyde or a ketone. You want a non-nucleophilic conjugate base. So be careful with the acid selection. You can't just throw in HCl. You've got to choose a big bulky base, usually that's resonance stabilized. All right, so now let's look at the mechanism. It's a bit more complicated. And I'm just going to stick with acetone. Like I said, this could be any aldehyde or ketone. I'm going to have two equivalents of methanol. And I'm going to have catalytic acid floating around. What do you think the first step's going to be? Protonation of the ketone. However, this is always going to be under equilibrium conditions. Students will ask me, doesn't it protonate the alcohol too? Absolutely. However, under equilibrium conditions, some of that carbonyl will get protonated. Okay, so in your next step, you've got your protonated ketone or aldehyde. You still have your methanol floating around, so I'll just show two separate ones now. And in the next step, your methanol is a weak nucleophile, but now you've got a really great electrophile because you protonated that ketone, right? So this can attack, kick up electrons. Oops, sorry, I'm drawing the same thing. And you've got your second equivalent of methanol hanging out. Now what you're going to do is move protons around. So I'm going to shorthand this as plus or minus H plus. And that's just my shorthand for shuttling a proton. In particular, it's going to be this proton, right? And this proton will just get moved over through proton transfers to the next door alcohol. So I'm just going to highlight it so we can keep track of where that proton's going. But do you see how it's moving over? That can be done by the solvent, which in this case is methanol. That's the most likely thing that's going to move that proton around. So I'm just going to trim down the number of steps we're showing. All right, the interesting thing here, though, is at this point, this is a good leaving group. And so in your next step, what you can do is clamp down on this, launch this off as a leaving group. And when you do this, you end up with a double bond to the carbon. You end up with water floating around, and you end up with methanol. Okay, in the next step, your second equivalent of methanol can attack in, kick up electrons onto that oxygen. Let me slide this over a bit. But the methanol that added in still has its proton floating around. So at the very end, what you're going to do is lose a proton. So I'll do minus H plus. To get to your final product. And water. All right, so it's a kind of steppy reaction. It's a bit complicated, and there's a lot to keep track of. If we look at this, water is the byproduct. And in this case, are we forming an acetal or a ketal? What do you guys think? A ketal, because it's the resulting product of a ketone. The important thing to remember is that ketals are formed when two equivalents of alcohols are added in. What happens if you stop with just one alcohol? Well, if that happens, as in the case with our pod, let's actually go back to the pod. If you notice in this one, we protonated our alcohol and we only could get one equivalent of our alcohol to add in. That's referred to as a hemi-acetal or a hemi-ketal, meaning it's halfway there. And we'll talk more about that later. Usually, though, you'll overshoot and go all the way to your ketal or acetal. Yep? Oh, that's a good question. Anytime you see a squiggly line like that, that means it's either axial or equatorial. It's both, meaning you're getting a mixture of products. Good question. And we'll, again, go back and talk about that hemi-acetal and ketal formation a little later. All right. So now I've got another question for you. Looking at this overall big complicated reaction mechanism, how can you really favor formation of your ketal? Does anybody have any ideas? What's that? Yeah, using a ketone. That will exclusively get you a ketal and not an acetal. That's a fair point. But how can we drive formation towards the right-hand side of the equilibrium, meaning our products? Perhaps heat. However, in this case, I would say there's other things you can do. If you remember yesterday, we talked about Le Chatelier's principle, and what were you saying about water? The amount of water, right? So let's imagine that we have a lot of water in this reaction mixture. Is it going to favor formation of the ketone or the ketal? Ketone, right? If you remember, Le Chatelier's principle says if you keep on adding in more of your byproduct, you'll actually push the reaction backwards. It's disfavorable, right? So what might be another trick with water? We don't want to add water. What would be the opposite? Remove it. So you can maybe distill water off of the reaction or try to trap it somehow to drive formation of your product. That's one trick you can do. What's another trick you could do? Not using water. Same idea, though. Yeah, increase the methanol concentration. If you increase the methanol concentration, you're going to push it more towards the product side. So there's a few different tricks you can do, but the key thing to remember is this is under equilibrium conditions, which means you follow Le Chatelier's principle. So let's make a note. Equilibrium position depends on concentration of water and or alcohol. Oh. So you can try to push this to that product side by removing water or flooding it with methanol. All right, so now let's take a look at some other examples. And another example is with cyclic acetals. All right, and I'll show you the idea behind this. Again, we're going to start out with acetone. It's the simplest one. And we're going to treat this with ethylene glycol. If you remember naming diols, we said ethylene glycol is called that because it's got the CH2 spacer in between two alcohols. This is commonly used in the formation of cyclic acetals. Again, you'll quite often react this with catalytic acid. So we've got our catalytic acid here. First step, just like before, under equilibrium conditions, some of your ketone or aldehyde will get protonated. Okay, and then in the next step, just like before, this can attack in, kick up electrons to that oxygen. Let me clean up my hydrogen here. And then in the next step, we're going to remove that proton, and this time I'm going to show all of the steps. So we're going to remove this whoa. Shoot. There we go. We're going to remove this proton. What would this be called as an intermediate? It's not a full acetal yet. It's not a full ketal, excuse me. We've only added one equivalent of alcohol in. So like I said, this is commonly referred to as a hemiketal. Meaning only one alcohol has attacked. We're only halfway there. Okay, so in our next step, again, to complete the proton transfer, I'm going to draw my equilibrium arrows. Sorry, that looks kind of bad. I don't know if that's any better, but you get the idea. We're going to add in a proton to the other oxygen, so it's going to steal this proton. All right, and just like before, you can kick that off, and the other alcohol present in solution is right here. So we'll have that attack and kick off that oxygen. All right. This is a little tricky to draw, but what we're doing is we're forming a ring system. It looks like this, plus water. And in the last step, we're going to try to remove that proton. It's coming off here. So I'll do minus H plus. And we end up with our final product plus water. So this is our cyclic ketal. And if you remember, water in this case is the byproduct. All right. So then the question is, well, what if we want to go in the reverse direction? We can flood the reaction with water and get it to go in the reverse direction. That's quite often the easiest approach to use. If you flood it with ethylene glycol, it's a lot harder to work with, so simply adjusting the concentration of water is the easiest thing to do at this point. Another thing that you'll see in the textbook is cyclic ketals are very unique. I call these protected ketones. Or aldehydes for that matter. But if you look at the cyclic ketal, it's no longer electrophilic. Nothing wants to attack it at this point. It's essentially going to be inert. So for example, if you try to attack this with a Grignard reagent, it's just going to stare at it. Nothing's going to happen, which is pretty handy. So I'll show you some cool concepts that can be applied. And I want you to problem solve this. So let's say we're doing this transformation. And it may require more than one step. But our goal is to make an alcohol. Can I just treat this with LAH? Why not? So if I treat this with LAH, what would happen? Yeah, exactly. LAH will actually reduce a ketone faster than it reduces an ester, which is a problem. We don't want the ketone to react. Okay, so that means we might need to protect our ketone. So for example, to get around this, I would say add in ethylene glycol and catalytic acid, maybe a little bit of sulfuric acid. And when you do this, you should be able to exclusively protect your ketone by tying it up in that ring system. The ester won't do anything. It'll just hang out there. And then in step 2, you can treat this with LAH, followed by quenching with water. That will reduce the ester because now your ketone's protected. But now we need to get to our final product, and how do we do that again? A lot of water, right? So flood it with water. We know Le Chatelier's principle says if you flood it with water, it will do the reverse reaction, but you still need that catalytic acid around. So water and catalytic acid will remove that protecting group. So it's a clever mechanism for protecting aldehydes and ketones. Does that make sense? It's kind of neat. So a similar method could be used if you wanted to exclusively react the ester with the Grignard reagent and not the ketone, you could protect it. There's a variety of situations where this comes in handy. Does that make sense? All right. Now we got to change gears into nitrogen nucleophiles. And this is pretty similar, but with a few twists. So I'll show you the overall transformation, and then we'll do the mechanism after. This time I'll use an aldehyde. and I'm going to use a primary amine. And it's important in this case that it's primary. And when you run this reaction, you still need some acid around, but we'll come back and talk about that acid because it actually is more complicated this time. When you do this, you essentially stop at the carbon-nitrogen double bond, and again, you kick off water. And in this case, it is called an imine. All right, I am going to make a note that the acid in this case matters a lot. In this case, you run this under a buffered condition, and the pH should be usually between 4 and 5. What do you think the problem is if we use something like sulfuric acid? Yeah, that'll be a pH of almost 0. But what do you think a competing reaction could be besides protonating the carbonyl on the aldehyde? Yeah, the nitrogen. We know amines are good bases, right? Ammonia is a classic example of a pretty good base. If you have a really strong acid around, you will protonate your amine and it will be the world's worst nucleophile. So the goal is to have just enough acid to facilitate the reaction, but not so much that you shut down the amine and it becomes unreactive. So you have to be very, very careful about the pH. And I'll just say you want to avoid trapping the amine by protonation. Does that make sense? It's an important distinguishing feature. So normally when you run these reactions, you'll just buy a buffer and use that. Or if you want to get fancy, you can make your own buffer. All right, so let's look at the mechanism. The mechanism's a little bit different than before. I'm going to color code it just like before with our primary amine. Instead of the acid protonating the carbonyl, we're going to show the amine attacking first. And when your amine attacks, it still has a positive charge. Okay? And then in the next step, what you need to do is a proton transfer. So I'm going to condense this down to one step and just say plus and minus H plus. And we'll kind of show the shuttling of a proton from one of the nitrogens over to the oxygen. And this is done usually by the solvent. Okay, so we're almost there. And then in the next step, what we need to do is protonate the alcohol. Just like before, after you do that, this is a leaving group. Hydroxide's a crummy leaving group, but water is an excellent leaving group. And so the next step, we can take a lone pair from this nitrogen, and we can shove off this leaving group. And then water gets kicked off. So that's our byproduct. And then in our last step, we're going to remove the proton coming off that nitrogen because we don't want that nitrogen to have a formal charge. And we end up with our imine and water. Does that make sense? So it is a little bit different. The main difference is with alcohols, we had to protonate the carbonyl first. In this situation, we didn't. There's also another reason why. So previously I said you don't want to overprotonate your amine, otherwise it will be trapped, can't act as a nucleophile. The other big difference is in this case, this amine that you're starting with is way more nucleophilic than an alcohol. Why are amines more nucleophilic than an alcohol? Does anybody know? Yeah, they're less electronegative. So let's make a note of that. Amines are more nucleophilic than alcohols due to electronegativity. Therefore, you don't have to protonate your ketone or aldehyde. So it is a little bit different. An analogous example too is with Grignard reagents, right? Carbon's even less nucleophilic, which means it can attack a ketone or an aldehyde without it being protonated. So it's kind of in between having an oxygen nucleophile and a carbon nucleophile. It doesn't need to be protonated for this to occur. Yep?
So are you saying that we should react with an H first, then protonation?
Yes, exactly. So the best way to show this mechanism is to show the amine the amine attack your aldehyde or ketone first, and then do proton transfers. You don't want to protonate the aldehyde first. We know that's unlikely to occur simply because a protonated ketone or aldehyde has a really, really low pH, and in order to do that, you have to have a really strong acid, and like I said, that will protonate your amine and make it stuck, so it won't attack. It won't even have a lone pair to attack with. Yeah, so it's kind of this interesting deviation. All right. I know it's complicated. We've got a couple more. If you notice, we've only been working with primary amines. We've got to do secondary amines next. I will say this is one of the most dense days of third term. So let's take a look at a secondary amine. And I'm going to do the overall reaction first. But just like before, we're going to have two R groups instead of just one this time. So this is a secondary amine. Again, this is going to typically be done under a buffered system. Buffer at approximately a pH of 4 to 5, so it's still acidic but not super acidic. And when you do this reaction, actually, sorry, I'm going to change this and add in the CH3 here. We'll just keep it simple. When you do this reaction, what you're going to do is form a new functional group that we haven't seen before. Looks like this. And you're going to kick off water. This is referred to as an enamine, not an imine. Does anybody know why it's called an enamine? It's not super creative. we've got an alkene in it, right? So it's an alkene amine, shorten it up to enamine, right? So you can kind of shorthand it that way. Honestly, that's how I remembered it when I took organic chemistry, and it stuck with me this far, so I figure it works. Amines don't have alkenes, so you can remember there's no en in there, right? So it's an easy way to remember. All right, so let's take a look at the mechanism and try to understand why it's different than the mechanism we saw with primary amines. All right, so just like before, we've got our amine floating around. I'm going to flip it around so that the R groups are on the right-hand side. And we said we don't want a really strong acid. The nitrogen is nucleophilic enough to attack first and kick up electrons onto the oxygen. So when the nitrogen adds in, that nitrogen has a positive charge. What we're going to do next is shuffle the proton around, just like before. Oh, let me keep the R's blue. And what do you think the next step is going to be after we do this shuffling of protons? Yeah, protonation where? Yeah, protonation of the alcohol. So we just shuffled one proton from that nitrogen to the oxygen. Now we need to add a second proton onto that alcohol. And the reason for that, like I said before, is right now we don't have a good leaving group. Okay, so this is going to steal a proton. OH2, this is positive. Got two blue R groups. We've got our good leaving group. Got a lone pair. Next step we know is going to be kicking off of that leaving group. You can label this as a leaving group, just to be thorough. And when we do this, we're almost there. Because I know your hand's probably tired at this point. However, unlike with the imine reaction, we can't just deprotonate that nitrogen to get a neutral compound, right? We're stuck. It has two alkyl groups coming off of it. It has no protons coming off that nitrogen. So the only option at this point is to do an elimination reaction that looks like this, right? So we're going to deprotonate and form an alkene. Let me fix this. Oh my goodness. Sorry, 1 second. Having an off day right now. I don't know why I'm struggling to put a double bond in the right spot. What's that? Thank you. I appreciate the moral support. All right, and when you do this, you generate your protonated water. which again makes that acid catalytic, but it's the only way to get to a neutral product here. It does rely on having protons in this position, right? So this only works if you've got protons over here. If you don't have protons over here, you actually get kind of stuck in a cationic intermediate. Does that make sense?
Could you just find out that amines attack both this year? Because I didn't see that last year.
So previously, I used to try to just keep it consistent to avoid confusion. It's been known for a while that it works this way. I was just trying to avoid confusion. This year, I wanted to be sure to teach it right and not just simplify it to make it easier. So unfortunately, it's more complicated this year than it was in previous years. Does that make sense? All right, I'll give you guys a practice problem, and then I think we'll probably stop after that. We won't go on to our next reactions today. So let's do a little bit of practice. Oh, sorry, so we'll do diethylamine this time. And again, we're going to run this under a buffered system. I want you to predict what product or products you will get out of this reaction. And if it's helpful, you may want to actually draw the full mechanism to double check. All right, let's just try to predict the products. I'm not going to show the full mechanism for this one, but be sure to practice it if you are struggling with it until you can do it without your notes as an aid. First thing I always do is I look at my amine and I try to determine whether or not I'm going to get an imine or an enamine. Which one do you think we're going to get? Enamine, right? So we've got a secondary amine. If we have a secondary amine, that means we must be getting an enamine. All right. Usually students have no problem predicting the first product, and they say one of them should look like this. Right? So we've got an alkene right next to that central carbon. That looks good. However, there's a second product, and it's an easy one to forget. Where it looks like this, right? So if we look at this, is that an E or a Z alkene? Z. Z same side, if you remember that. This one's an E alkene. All right, what's the relationship between these? Are they enantiomers, diastereomers, constitutional isomers? How would we describe them? Diastereomers, right? They're non-superimposable mirror, or they are not non-superimposable mirror images. They're arranged completely differently. So these are a mixture of diastereomers. So with diastereomers, will these be easy to separate from one another, or will they be difficult to separate? Do they have same physical properties? No, they don't. So in this case, you can easily separate them using things like chromatography, distillation, things like that. So it is nice in that regard, unlike reactions where we get a mixture of stereocenters, where it's R and S. Those are enantiomers usually. Those are difficult to separate. These are a lot easier. It's really hard to tell, because if we look at this one over here, that's got a steric clash. And if we look over here, we also have a steric clash. So it's like, well, what do we want? Do we want a steric clash here, or do we want a steric clash here? It really depends on the size of the groups that are attached. So I don't want to tell you that one's always going to be major over the other. It really depends on the size of the groups. Yeah. Great question, though. Yeah. All right. One last thing before we head out is some other nitrogen nucleophiles. We're not going to do full mechanisms, but I did want to show them. the first one is when you have a ketone or an aldehyde, you can take an amine, that also contains an alcohol. And these are called hydroxyamines. And then the question is, well, which one's going to be more nucleophilic, the nitrogen side or the oxygen side? Nitrogen. We've already said nitrogens are more nucleophilic. All right, looking at this, are we going to get an imine or an enamine? An imine, right? It's a primary nitrogen. So we can go ahead and we can say, all right, with catalytic acid, and like we said, this is normally done under buffered conditions. Let me clean this up. Make something that looks like this and kick off water as a byproduct. These are called oxamines, right? And that simply has to do with the fact that nitrogens are more nucleophilic than oxygens because they're less electronegative. They don't hold on to their lone pair as tightly. There's one last one, and I'll let you go and rest your hand. And this is where we will pick up tomorrow. This is called hydrazine. Do you think it's going to form a cyclic ring system, like with the oxygen we saw previously? I'd say no. That would be a three-membered ring. That's very, very strained. So unlike what we saw with the oxygen nucleophiles, it'll stay at the imine. We'll kick off water. And this is referred to as a hydrazone. And these are really versatile intermediates. The one tricky thing with these is hydrazine is highly flammable. In fact, they used to use it as rocket fuel. So it is a little logistically challenging to carry out, especially on a large scale. But it is really useful in a reaction that we'll cover tomorrow. So that's where I'll stop today. The problem of the day is somewhat challenging. I would recommend trying to work with a partner on it and try to get started today rather than tomorrow, 15 minutes before class.